In this video, I'm going to be presenting a method for solving linear first-order differential equations with variable coefficients. To start off, let's say we have an object falling through the air with different parameters affecting the contributions of forces acting on it. And we want to come up with a differential equation to describe the motion of the object falling through the air. Here we're going to be taking into account an upward force of drag and a downward force due to gravity. Introducing the quantities that we're going to be using to model this problem, we have the drag coefficient, we have v for velocity, which is our dependent variable, and v is going to change with time because we're going to be modeling the motion of this object during a certain time interval. So we're going to have the independent variable t, for which the velocity v changes, and we're going to have m for the mass of the object and g for the acceleration due to gravity. Okay, and again, we know we want to come up with a differential equation to describe the motion of the object. So from Newton's second law, we know that F equals m times a, or mass times acceleration. And we know that we can rewrite acceleration as dv dt. So F equals m times dv dt. And in this model, we want to sum up the net force, which will be equal to the upward contribution of force from drag plus the downward contribution from gravity. So we now have m times dv dt is equal to mass times the acceleration due to gravity minus the contribution from drag. And then solving an equation, as in equation 4, we're looking for a differentiable function y that satisfies equation 5, which is dy dt equals fty. Okay, again we have equation 4, which is m times dv dt, or the acceleration, is equal to mg minus the drag coefficient times velocity. And we can say that this equation is a more general form. Dy dt is equal to minus a times y plus b. So here's our coefficients here, our constants, a and b. This can be further generalized and written in terms of arbitrary functions of t. So we have in equation 7, dy dt plus p of t times y is equal to g of t. And what we've done here is we've rewritten the equation in a more standard form. So we've written the equation in terms of a general first order linear differential equation. And we're basically doing this because it makes the problem easier to solve, because there's no one size fits all way of solving differential equations. So there's little methods and tricks to solving each type of equation. And for this specific equation, it works out better if we put it in this form. Again, we're solving for y. And to do that, so to solve, we want to rewrite equation 6 in terms of equation 7. So we want to take the equation with the constants a and b and then rewrite it in terms of the standard form that you can find in 7. And then we're also going to multiply by a factor mu of t to get equation 8. Equation 8 is dy dt times mu of t plus a times y times mu of t equals b times mu of t. And that's equation 8, where we've applied a factor. We've multiplied this factor to equation 7. So we've multiplied mu of t to equation 7. Or I should say, an equation of the form of equation 7. And the overall intention here is that we want to integrate equation 8, without knowing why. And in order to do so, we can compare the left side of equation 8 with differentiation formula equation 9. So equation 9 is mu of t times dy dt plus d mu of t dt times y. And if you compare that to equation 8, the left side of equation 8, you can see that the first terms are the same, and we can match the second term if we note that d mu of t dt is equal to a mu of t. Then we can say d mu of t dt over mu of t is equal to a, which is equivalent to saying d dt natural logarithm of the absolute value of mu of t is equal to a. We can then integrate and get the natural logarithm, the absolute value of mu of t is equal to at plus c. Or we can write mu of t is equal to c e a times t. And I think equation 15 got a cutoff there on the video. So you can rewrite equation 14 as mu of t is equal to c times e a times t. And that's our new mu of t. And we're going to take this new mu of t and we're going to substitute that value into equation 8. And we're going to get e a times t times dy dt plus a times e a times t times y equals e a times t multiplied by the arbitrary function g of t that was, if you went back to which equation? If you went back to equation 6, that would correspond to b. So b is now analogous to the function g of t. And then we can use the differentiation formula that was noted in equation 9, and we get equation 17. So d dt of e a times t times y is equal to e a times t multiplied by the function g of t. And then we can integrate and we get e a times t multiplied by y is equal to the integral of e a times s multiplied by g ds plus c, and that's going to be equation 17. And then to get the general solution, we have y equals e minus a times t multiplied by the integral of e a times s multiplied by g ds plus e minus a times t. And in equation 18, we've used the integration variable s to separate it apart from the independent variable t.